Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why space is nearly empty? When you look up at the night sky, space appears crowded with stars, planets, and galaxies. Photographs from telescopes show spectacular images of colourful nebulae, dense star clusters, and brilliant galaxies packed with hundreds of billions of stars. These images create an impression of a cosmos teeming with matter, a universe filled to the brim with celestial objects. But this impression is profoundly misleading. Space is almost unimaginably empty. The distances between objects are so vast and the objects themselves so small relative to those distances that if you could somehow travel to a random location in the universe, the overwhelming likelihood is that you would find yourself surrounded by nothing. No stars, no planets, no gas, no dust, for distances stretching farther than you could travel in a lifetime, even at the speed of light. To understand just how empty space is, consider the space between Earth and the Moon. The Moon orbits at an average distance of about 380,000 kilometers from Earth. That's far enough that you could fit all the other planets in the solar system side by side in the gap between Earth and the Moon, with room to spare. Now imagine taking a sphere with a radius equal to this Earth-Moon distance. Within that enormous volume, there are only two objects of any significant size, Earth and the Moon themselves. Everything else is emptiness, with only occasional atoms of gas or tiny dust particles scattered throughout. The situation becomes even more extreme when you consider the space between planets. Earth orbits about 150 million kilometers from the Sun. Mars orbits about 230 million kilometers from the Sun. The distance between Earth and Mars varies as both planets orbit, but at their closest approach, they're separated by about 55 million kilometers. This vast gulf contains essentially nothing. No planets, no moons, just a scattering of asteroids so small and so far apart that even if you were travelling through this region, you would be extraordinarily unlikely to come anywhere near one. The asteroid belt, often depicted in science fiction as a dense field of tumbling rocks that spaceships must carefully navigate, is in reality astonishingly sparse. The belt contains hundreds of thousands of asteroids larger than 1 kilometer across and millions of smaller ones. This sounds like a lot, and by the standards of everyday experience it is. But these asteroids are spread across an enormous volume of space, a region extending from about 300 million kilometers to 500 million kilometers from the Sun, and spanning the full circumference around the Sun at these distances. The result is that the average distance between asteroids is measured in millions of kilometers. If you were to travel through the asteroid belt, you would see nothing for days or weeks of travel before coming near even a single asteroid. The density of matter in the asteroid belt averages far less than 1 particle per cubic kilometer. Compare this to air at sea level on Earth, which contains about 10 to the 25th particles per cubic kilometer, a 1 followed by 25 zeros. The asteroid belt, despite containing countless asteroids, is millions of billions of times less dense than the air you're breathing right now. Every spacecraft we've sent through the asteroid belt, and many have made the journey, has passed through without incident, without needing to dodge asteroids, simply because the belt is so incredibly empty. Beyond the planets, the emptiness becomes even more profound. The nearest star to our Sun, Proxima Centauri, lies about 40 trillion kilometers away, a distance so vast that light, travelling at 300,000 kilometers per second, takes over 4 years to cross it. If you scaled the Sun down to the size of a basketball, Earth would be a grain of sand orbiting about 25 meters away, and Proxima Centauri would be another basketball more than 6,000 kilometers away. The sphere of space between these two basketballs contains essentially nothing. No planets, no asteroids, no comets that we know of, just occasional atoms of hydrogen, some dust particles so rare you could travel for years without encountering one, and the faint pressure of starlight. This interstellar space contains gas, but calling it gas seems almost misleading given its extreme tenuousness. In the space between stars, the density averages about 1 atom per cubic centimetre. For comparison, air at sea level contains about 10 to the 19th atoms per cubic centimetre. Interstellar space is less dense than air by a factor of 10 million trillion. The best vacuum we can create in laboratories on Earth, in the most sophisticated vacuum chambers, is still millions of times denser than the average density of interstellar space. Even the densest regions of interstellar space, the molecular clouds where stars form, are extraordinarily sparse by terrestrial standards. These clouds, which appear dark and opaque in photographs because they block light from stars behind them, contain perhaps 1 million atoms per cubic centimetre at their densest cores. This is dense for space, but it's still 10 trillion times less dense than air on Earth. You could travel through the densest part of a molecular cloud and not even notice. There would be no resistance to your motion, no sense of passing through anything. The emptiness extends to larger scales as well. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, along with vast quantities of gas, dust, and dark matter. Yet these hundreds of billions of stars occupy a disk about 100,000 light-years across and roughly 1,000 light-years thick at the Sun's location. The stars are so far apart that if you were to travel to a random location within the galaxy, you would find yourself in interstellar space, far from any star. The average distance between stars is about 5 light-years. At the scale where stars are separated by light-years, the stars themselves, objects typically about 1 million kilometers across, are essentially point-like. They occupy a negligible fraction of the galaxy's volume. Between galaxies, the emptiness reaches its most extreme. The space separating galaxies is called intergalactic space, and it's even emptier than interstellar space. The density of matter in intergalactic voids, the enormous empty regions between galaxy clusters, is approximately 1 atom per 10 cubic meters. Think about that. You could take a cube of space 10 meters on each side, large enough to contain a small house, and on average, it would contain just 1 single atom. This is as close to perfect vacuum as nature achieves anywhere in the universe. The scale of intergalactic distances staggers comprehension. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, lies about 2.5 million light-years away. The space between our galaxy and Andromeda is largely empty, except for a few dozen small dwarf galaxies and some scattered gas clouds. Beyond our local group of galaxies, the distances grow even more immense. The Virgo cluster of galaxies, which contains thousands of galaxies, lies about 50 million light-years away. The space between galaxy clusters is measured in tens of millions to hundreds of millions of light-years, and it contains essentially nothing. So why is space so empty? The answer lies in how the universe evolved after the Big Bang. In the earliest moments, the universe was actually extremely dense. All matter and energy were compressed into a tiny volume. But the universe has been expanding ever since, and as it expands, the matter within it spreads out, becoming less and less dense. The expansion of space itself increases the distances between objects, diluting the average density of matter throughout the cosmos. Gravity works against this dilution by pulling matter together into clumps. Regions that were slightly denser than average in the early universe attracted more matter, becoming denser still, while regions that were slightly less dense lost matter to the denser regions and became emptier. Over billions of years, this process created the structure we see today. Matter concentrated into stars, which are concentrated into galaxies, which are concentrated into galaxy clusters and superclusters with vast voids between them. But even with gravity concentrating matter into structures, the vast majority of space remains empty because the fundamental ratio of matter to space is so low. If you took all the matter in the observable universe, every atom in every star, planet, gas cloud and galaxy, and spread it uniformly throughout all of space, the density would be about 5 atoms per cubic meter. This is the average density of the universe, and it reveals that matter is extremely rare. The universe is about 5 atoms of matter per cubic meter on average, with the rest being empty space and dark energy. The emptiness of space has profound implications. It means that collisions between stars are extraordinarily rare, even in the centers of galaxies, where stars are most densely packed. When 2 galaxies collide, and galaxy collisions are fairly common on cosmic timescales, the stars themselves almost never hit each other. The galaxies pass through each other, like 2 clouds of gnats interpenetrating, without individual gnats colliding, because the distances between stars are so large compared to the stars' sizes. The emptiness also means that space travel is, in some ways, easier than it might otherwise be. A spacecraft travelling through space doesn't need to constantly dodge debris or navigate through fields of material. Space is clear. The challenges of space travel come not from crowding but from the vast distances between destinations and the energy required to cross those distances. Light from distant objects travels through this emptiness for billions of years, crossing intergalactic voids, interstellar space, and the relative crowding of planetary systems to eventually reach our telescopes. The fact that we can see distant galaxies at all, objects billions of light years away, testifies to how empty space is. If space were filled with gas or dust at densities even remotely approaching terrestrial conditions, the light would be scattered and absorbed long before travelling such distances. The emptiness of space is not a coincidence or an accident. It's a fundamental consequence of the universe's expansion, the initial density of matter after the Big Bang, and the way gravity organises that matter into structures. The spectacular images of galaxies, nebulae, and star clusters show us the rare locations where matter has concentrated. But these are the exceptions, the islands of matter in an ocean of emptiness. The typical state of the universe is not the crowded star field or the dense nebula. It's the dark, cold, nearly perfect vacuum of intergalactic space, where a single atom might drift alone for years before encountering another, where the nearest star is so distant that its light takes millions of years to arrive, and where the overwhelming reality is not presence but absence, not matter but void, not something but nothing, extending in all directions for distances that dwarf the span of human comprehension. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. but this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's centre. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometre and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into 2 or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scale with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet, rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. Rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second to reach low Earth orbit, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond. How life could survive on rogue planets. Most planets orbit stars, bathed in starlight that provides warmth and energy for any life that might evolve. But scattered throughout the galaxy are worlds that wander alone through the darkness of interstellar space. Rogue planets, ejected from their birth solar systems through gravitational interactions, or perhaps forming in isolation, drifting for billions of years without a sun to orbit. These orphaned worlds seem like the least hospitable places imaginable for life. Cut off from starlight, they receive no external heat source, no energy for photosynthesis, no warming to maintain liquid water on their surfaces. Yet despite these apparently insurmountable obstacles, life might still find ways to survive on rogue planets, drawing on internal heat sources, subsurface environments, and the remarkable adaptability that evolution has demonstrated countless times on Earth when organisms colonize seemingly impossible habitats. The key to habitability on rogue planets is internal heat. Unlike stars, which generate heat through nuclear fusion, rogue planets must rely on residual heat from formation and ongoing heat from radioactive decay of elements in their interiors. When planets form, the process of accretion, countless collisions between smaller bodies that gradually build up the planet, converts kinetic energy into heat. Additionally, gravitational compression, as material piles up, releases energy that heats the planet's interior. A newly formed planet is molten or partially molten, taking millions to billions of years to cool. This primordial heat, combined with heat from radioactive decay of uranium, thorium, potassium, and other radioactive isotopes in the planet's rocks, keeps planetary interiors warm for billions of years. Earth itself generates about 47 terawatts of internal heat, roughly equal to 10,000 large power plants operating continuously. Most of this heat comes from radioactive decay, with some contribution from residual primordial heat and from crystallization of Earth's molten iron core. This internal heat drives plate tectonics, powers volcanic activity, and maintains Earth's magnetic field. A rogue planet of similar size and composition would generate similar amounts of internal heat, regardless of whether it orbits a star or drifts through interstellar space. The challenge is keeping that heat trapped. Without an atmosphere, heat would radiate directly into space, and the planet's surface would quickly reach temperatures only a few degrees above absolute zero. The background temperature of the universe, about -270 degrees Celsius. But a substantial atmosphere could act as insulation, trapping heat through the greenhouse effect and maintaining warmer temperatures at the surface or in the lower atmosphere, even without any external heat source. A rogue planet with a thick hydrogen atmosphere could potentially maintain surface temperatures warm enough for liquid water through atmospheric pressure and greenhouse warming alone. Hydrogen is the lightest and most abundant element in the universe, and large planets can capture and retain massive hydrogen envelopes during formation. The greenhouse effect from a thick hydrogen atmosphere, combined with internal heat radiating from below, could create a temperature profile that allows liquid water to exist at the surface or at some depth within the atmosphere, where pressure and temperature are both suitable. Computer models suggest that a rogue planet several times Earth's mass, with a hydrogen atmosphere perhaps 100 times more massive than Earth's atmosphere, could maintain surface temperatures above the freezing point of water for billions of years, powered only by internal heat. Such a planet would be entirely dark at the surface, no day or night, just eternal darkness. But it would be warm enough for liquid water, and where there's liquid water and a source of energy, life becomes possible. Life on such a world could not depend on photosynthesis, but that's not necessarily a problem. On Earth, entire ecosystems exist in permanent darkness, sustained by chemosynthetic bacteria that extract energy from chemical reactions rather than sunlight. Deep-sea hydrothermal vents host thriving communities where bacteria oxidize hydrogen, sulfide, methane, or hydrogen, using the chemical energy to build organic molecules from carbon dioxide. These chemosynthetic bacteria form the base of food chains that support tube worms, clams, fish, and crustaceans, all living in absolute darkness, kilometers beneath the ocean surface. A rogue planet with liquid water oceans, maintained by internal heat and atmospheric greenhouse warming, could develop similar chemosynthetic ecosystems. Volcanic activity would vent gases like hydrogen, hydrogen sulfide, methane, and carbon dioxide into the water and atmosphere. Bacteria could evolve to extract energy from these chemicals, building organic molecules that could support more complex organisms. The entire biosphere would operate on chemical energy from the planet's interior rather than solar energy, making the planet's life forms independent of any star. Subsurface oceans represent an even more plausible habitat for life on rogue planets. Many worlds in our solar system likely have liquid water oceans beneath ice shells. Europa, Enceladus, possibly Titan, Ganymede, Callisto, Pluto, and other bodies. These oceans are kept liquid by tidal heating from their parent planets, or by internal radioactive heating. A rogue planet with sufficient internal heat and a thick ice shell could maintain a subsurface ocean indefinitely, with the ice providing insulation that prevents the ocean from freezing while protecting it from the harsh radiation and extreme cold of interstellar space. The ice shell on a rogue planet might be very thick, perhaps tens or hundreds of kilometers, creating an insulating layer that traps internal heat far more effectively than any atmosphere. The ocean beneath this ice would be completely dark, protected from the radiation that fills interstellar space, and stable for billions of years. Temperature would be maintained by heat flowing from the rocky mantle below. Hydrothermal vents on the ocean floor would provide chemicals and energy for chemosynthetic life. Such an ocean might be an ideal habitat, more stable than surface oceans on planets orbiting stars where stellar evolution, asteroid impacts, and climate variations create periodic catastrophes. Life in a subsurface ocean on a rogue planet would never know stars exist. The entire biosphere would be confined to the dark ocean, with the ice ceiling above and rocky floor below defining the limits of the habitable universe. Evolution would never produce eyes sensitive to visible light because no visible light exists. Organisms might instead evolve chemical sensing, pressure sensing, electroreception, or other non-visual senses. Intelligence, if it evolved, would develop without ever seeing stars, planets, or anything beyond the ocean's boundaries. Such a civilization might not even realize that a larger universe exists beyond their world, having no way to detect or observe the space around them through kilometers of ice. Geothermal pockets could create localized habitable zones even on rogue planets without global oceans. Volcanic activity or concentrations of radioactive elements could heat specific regions, melting ice to create underground lakes or pockets of liquid water embedded in ice. These isolated water bodies might be small, perhaps only a few kilometers across, but they could persist for millions of years, long enough for life to evolve and diversify within each pocket. Different pockets might develop different ecosystems in isolation from each other, creating multiple independent evolutionary experiments on a single rogue world. Atmosphere composition would profoundly affect habitability. A rogue planet that retained or captured a hydrogen-helium atmosphere during formation could use that atmosphere's greenhouse effect to maintain warmth. Carbon dioxide, methane, and ammonia are all more effective greenhouse gases than hydrogen and would enhance warming at much lower atmospheric masses. A rogue planet with a thick carbon dioxide atmosphere and substantial internal heat might maintain temperatures warm enough for liquid water with a much thinner atmosphere than a hydrogen-dominated world would need. The size of the rogue planet matters significantly. Larger planets generate more internal heat from radioactive decay simply because they contain more radioactive material. Larger planets can also hold thicker atmospheres through stronger gravity and lose heat more slowly because their surface area to volume ratio is smaller. Heat escapes through the surface, but heat is generated throughout the volume, so larger planets stay warm longer. A rogue super-Earth several times, Earth's mass might remain habitable for far longer than an Earth-mass rogue planet, potentially maintaining surface or subsurface liquid water for tens of billions of years or more. Very small rogue planets, Mars-sized or smaller, would struggle to maintain habitability. They would cool quickly, losing internal heat within a few billion years. Their weak gravity would allow atmospheric escape, making it difficult to maintain the thick atmospheres needed for greenhouse warming. However, even small rogue worlds might maintain subsurface liquid water in deep aquifers or isolated pockets warmed by concentrations of radioactive elements or by residual heat from formation for some period after being ejected from their parent system. The abundance of rogue planets remains uncertain, but some estimates suggest they might outnumber stars. If planets are commonly ejected during the chaotic early phases of planetary system formation, the galaxy might contain billions or even trillions of rogue planets drifting through interstellar space. Most would be cold, dark, and apparently lifeless at their surfaces, but some fraction might maintain subsurface oceans or possess the right combination of size, composition, and atmosphere to support life in hidden biospheres, beneath ice or in dark surface oceans sustained by nothing more than the planet's internal warmth. Detecting life on rogue planets would be extraordinarily challenging. These worlds emit no reflected starlight, making them nearly impossible to detect through traditional astronomical methods. They can only be detected through gravitational microlensing. When a rogue planet passes in front of a distant star from Earth's perspective, its gravity briefly magnifies the star's light, or through direct detection of their infrared emission, the faint heat radiating from their surfaces. Neither method provides information about atmospheres, surface conditions, or potential habitability, let alone biosignatures. Future infrared telescopes might be able to detect the warmest rogue planets and potentially characterize their atmospheres if those atmospheres are thick enough to produce detectable spectral features. Finding methane, carbon dioxide, or other gases in unexpected ratios might hint at biological activity, though distinguishing biological from geological sources would be nearly impossible without additional information. Direct exploration by spacecraft seems impractical, given the vast distances between stars and the difficulty of even locating rogue planets, let alone traveling to them. The evolutionary trajectory of life on rogue planets might differ fundamentally from life on planets orbiting stars. Without the regular day-night cycle that drives circadian rhythms on Earth, organisms would have no reason to evolve timekeeping mechanisms tied to planetary rotation. Without seasons caused by axial tilt and orbital motion, there would be no seasonal cycles, no annual rhythms. Life would exist in an eternal, unchanging environment, at least on timescales shorter than geological epochs, potentially leading to very different evolutionary pressures than life on Earth experiences. The isolation of rogue planets creates another interesting possibility. These worlds might serve as interstellar arcs, carrying life between star systems. If a planet with a biosphere is ejected from its home system, life on that planet doesn't necessarily die. If the planet maintains subsurface oceans, through internal heating, life in those oceans could survive indefinitely, potentially for billions of years, as the planet drifts through the galaxy. Eventually, such a planet might be captured by another star system, or it might pass close to a star that warms the planet temporarily, allowing surface life to revive if it was dormant. This mechanism, planets carrying life between star systems, represents a form of panspermia that could spread life throughout the galaxy. How life could survive on rogue planets demonstrates the resilience and adaptability of biology when provided with even minimal requirements. Liquid water, chemical energy, raw materials, and time. A rogue planet cut off from all starlight, drifting through the darkness of interstellar space for billions of years, seems like an impossible place for life. Yet internal heat and thick atmospheres, or ice shells, could create hidden habitats where chemosynthetic ecosystems thrive in eternal darkness, where evolution operates unconstrained by day-night or seasonal cycles, where intelligent beings might arise never knowing that stars exist, and where life demonstrates its ultimate independence from sunlight, proving that biology requires not a sun to orbit, but merely the right chemical conditions and energy sources, expanding the definition of habitable environments to include not just planets in stellar habitable zones, but potentially countless dark worlds adrift in the spaces between the stars, each one a potential harbour for life in the vast ocean of the galaxy. How the moon pulls on Earth's oceans. Twice each day, the ocean rises up beaches and coastlines around the world, then retreats back toward the sea. This rhythmic rise and fall of the tides has shaped human civilization for thousands of years, governing when ships could enter harbours, when fishermen could gather shellfish from tidal pools, and when coastal communities needed to prepare for high water. The connection between these tides and the moon was recognised in ancient times, but understanding exactly how the moon creates tides requires thinking carefully about gravity, how it varies with distance, and how Earth's ocean responds to forces that stretch and squeeze it in complex ways. The fundamental cause of tides is gravity, but not gravity in the simple sense of the moon pulling water toward itself. If that were the entire story, we would see one bulge of water on the side of Earth facing the moon, and that would be the end of it. Instead, we observe two tidal bulges, one on the side facing the moon and another on the opposite side of Earth. This puzzling fact confused natural philosophers for centuries, until Isaac Newton, in his Principia Mathematica, published in 1687, provided the correct explanation using his law of universal gravitation and his laws of motion. The key insight is that the moon's gravity pulls on every part of Earth, but it pulls with different strengths depending on distance. The side of Earth closest to the moon experiences stronger gravitational attraction than Earth's centre, which in turn experiences stronger attraction than the far side. This difference in gravitational force across Earth's diameter creates what are called tidal forces, forces that try to stretch Earth along the line, connecting it to the moon, while simultaneously squeezing it perpendicular to that line. Imagine Earth's structure for a moment. The solid rock of Earth's crust and mantle resists deformation quite strongly. While tidal forces do deform the solid Earth slightly, raising and lowering the ground by about a foot, the effect is not dramatic because rock is stiff and strong. The oceans, however, are fluid. They can flow freely in response to forces, and they respond readily to the tidal forces that the solid Earth largely resists. Consider a point on Earth's surface directly beneath the moon. The water at this location is about 4,000 miles closer to the moon than Earth's centre. The moon's gravitational pull weakens with distance according to an inverse square law. Double the distance and the force becomes 1/4 as strong. This means the ocean on the near side experiences a gravitational pull toward the moon that's about 7% stronger than the pull experienced by Earth's centre. This differential force pulls the ocean away from Earth's centre, creating a bulge of water on the moon-facing side. Now consider the opposite side of Earth, the point farthest from the moon. Here the ocean is about 4,000 miles farther from the moon than Earth's centre. The gravitational pull from the moon at this location is about 7% weaker than at Earth's centre. Earth's centre is being pulled toward the moon more strongly than the water on the far side, effectively pulling Earth away from the water and leaving the water behind. The result is another bulge on the side opposite the moon. This creates the characteristic two-bulge pattern. If you could freeze time and look at Earth from space, you would see the oceans slightly elongated along the Earth-Moon line, with high water on both the near and far sides and low water at the points 90 degrees away from the moon. As Earth rotates beneath these bulges, any given point on Earth's surface passes through 2 high tides and 2 low tides each day, though not exactly every 12 hours, because the moon is also moving in its orbit, shifting the position of the bulges over time. The height of these tidal bulges would be quite modest if they responded only to the moon's gravitational pull, perhaps a foot or 2 in the open ocean. But the actual tides we observe at coastlines can be dozens of feet high. This amplification occurs because of the way ocean basins are shaped and because of resonance effects as water sloshes back and forth in confined spaces. The Bay of Fundy in Canada experiences the world's highest tides, sometimes exceeding 50 feet, because the bay's shape and size create a natural resonance that amplifies the tidal forcing from the moon and sun. The sun also creates tides on Earth, though they're smaller than lunar tides despite the sun's vastly greater mass. The reason is distance. The sun is about 400 times farther from Earth than the moon, and tidal forces depend not just on mass but on how much the gravitational pull varies across Earth's diameter. The sun's great distance means its gravitational pull varies less across Earth than the moon's does, making solar tides about 46% as strong as lunar tides, a ratio that Pierre-Simon Laplace calculated in detail in his comprehensive work on celestial mechanics in the late 1700s. The interaction between solar and lunar tides creates the familiar spring and neap tide cycle. When the moon and sun align, either on the same side of Earth during a new moon or on opposite sides during a full moon, their tidal effects add together, creating spring tides with especially high tides and especially low tides. The name has nothing to do with the season, but comes from the idea that the tides spring forth. When the moon and sun are at right angles as seen from Earth during first and third quarter moons, their tidal effects partially cancel, creating neap tides with smaller tidal ranges. This 2-week cycle of spring and neap tides is predictable and was well understood by ancient mariners, though they lacked Newton's gravitational explanation for why it occurred. The timing of tides is not as simple as one might expect. If you observe the tides at any coastal location, you'll notice that high tide doesn't occur exactly when the moon is overhead or exactly when it's on the opposite side of Earth. There's typically a delay of several hours called the tidal lag. This occurs because the ocean cannot respond instantaneously to the changing tidal forces. Water has inertia, it takes time to accelerate and decelerate, and friction between the moving water and the ocean floor dissipates energy, creating phase lags between the tidal forces and the ocean's response. These friction effects have profound long-term consequences. As tidal bulges try to follow the moon, but are dragged forward slightly by Earth's rotation, they create a gravitational pull on the moon that's not perfectly aligned with the Earth-Moon line. This misaligned pull acts to accelerate the moon in its orbit, gradually increasing its orbital energy and causing it to move away from Earth. Precise laser ranging measurements using reflectors left on the moon by Apollo astronauts have confirmed that the moon is receding from Earth at about 1.5 inches per year. This recession cannot continue indefinitely at the current rate. As the moon moves farther away, tidal effects weaken, slowing the recession. But over the 4.5 billion years since the moon formed, likely from debris created when a Mars-sized object collided with the young Earth, the moon has moved substantially farther from Earth. Early in Earth's history, when the moon was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles, tidal forces were enormously stronger. Tides might have been hundreds of feet high, and the moon would have appeared many times larger in the sky, looming over the horizon like an enormous sphere dominating the heavens. The energy dissipated by tidal friction doesn't just affect the moon's orbit, it also affects Earth's rotation. The gravitational drag from the tidal bulges acts to slow Earth's rotation gradually. Each century, Earth's day lengthens by about 1.7 milliseconds. This seems negligible, but over geological time, it accumulates. Fossil evidence from ancient corals, which show daily growth bands much like tree rings, indicates that 400 million years ago, Earth's day was only about 22 hours long, and a year contained about 400 days. The moon was closer, Earth rotated faster, and tides were stronger. This tidal interaction between Earth and the moon is an example of tidal locking in progress. The moon is already tidally locked to Earth, always showing the same face toward Earth because tidal forces from Earth have synchronized the moon's rotation period with its orbital period. Earth is gradually becoming tidally locked to the moon as well, though this process will take tens of billions of years to complete, longer than the remaining lifetime of the Sun. If it could be completed eventually, Earth would always show the same face to the moon, and the moon would hang stationary in the sky over one hemisphere, never visible from the other. Other bodies in the solar system experience even more extreme tidal effects. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated internally by tidal flexing. As Io orbits Jupiter in an elliptical path, the tidal forces it experiences vary in strength, squeezing and stretching the moon's interior. This constant kneading generates tremendous heat through friction, keeping Io's interior molten and driving its spectacular volcanic eruptions. This process, predicted by Stanton Peele and colleagues just before the Voyager spacecraft discovered Io's volcanism in 1979, is called tidal heating. Saturn's moon Enceladus experiences similar tidal heating, though less extreme than Io. The heat from tidal flexing keeps a subsurface ocean liquid beneath Enceladus's icy crust, and tidal stresses crack the ice at the South Pole, allowing geysers of water to erupt into space. Europa, another moon of Jupiter, likely has its subsurface ocean maintained by tidal heating as well, making it one of the most promising places to search for life beyond Earth. Tidal forces can also be destructive. Every large body creates a tidal limit, called the Roche limit, after Edouard Roche, who calculated it in 1848, inside which tidal forces exceed the self-gravity holding a satellite together. A moon that wanders inside the Roche limit will be torn apart by tidal forces, pulled into fragments that spread into a ring around the planet. Saturn's magnificent ring system may have originated this way, from a moon that either formed inside the Roche limit or migrated inward and was disrupted. Tidal forces operate throughout the universe. Binary stars experience tides that can transfer mass from one star to its companion. Black holes create tidal forces so extreme that they can tear apart stars that pass too close, creating spectacular tidal disruption events. Galaxies passing near each other experience tidal forces that stretch them into long streams of stars, creating the tidal tails visible in many interacting galaxies. The same physics that causes ocean tides on Earth, the differential pull of gravity across an extended object, operates on scales from moons and planets to stars and galaxies. The tides we observe at the beach are the local manifestation of a cosmic dance between Earth and Moon, a gravitational interaction that has been occurring since the Moon formed and will continue for billions of years into the future. Every incoming wave, every tide pool exposed at low tide, every ship waiting for high water to enter harbour is part of this larger story of how gravity shapes the motion of celestial bodies and how the Moon, our constant companion in the night sky, continues to sculpt the behaviour of Earth's oceans through the subtle but inexorable pull of tidal forces. The biosignatures that reveal living planets. Detecting life on distant planets represents one of the greatest challenges in astronomy. We cannot visit these worlds, cannot scoop up soil samples, cannot peer through microscopes at alien microbes. Most exoplanets appear as nothing more than tiny dips in their star's brightness as they transit, or slight wobbles in the star's position caused by the planet's gravitational pull. Yet from these minimal observations, measurements of light passing through a planet's atmosphere during transit, analysis of the planet's reflected light, characterization of its temperature and size, astronomers hope to determine whether life exists on worlds many light years away. The key lies in biosignatures, detectable signs that life is present, chemical or physical features that cannot easily be explained by non-biological processes, and that point toward the presence of living organisms modifying their planet's environment in measurable ways. Oxygen stands as the most famous biosignature, the gas that astronomers most eagerly search for in exoplanet atmospheres. On Earth, oxygen makes up 21% of the atmosphere, a concentration vastly higher than would exist without life. Oxygen is highly reactive. It combines readily with rocks, organic molecules, and other materials, removing oxygen from the atmosphere unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria use sunlight to split water molecules, releasing oxygen as a waste product. Without this biological production, Earth's atmospheric oxygen would disappear within a few million years as it reacted with surface materials. Detecting oxygen in an exoplanet's atmosphere would strongly suggest the presence of photosynthetic life, though not definitively. Oxygen can be produced through non-biological processes, photodissociation of water vapor by ultraviolet light, for instance, can split water molecules and release oxygen. But these abiotic processes typically produce only small amounts of oxygen compared to the abundant oxygen that photosynthesis generates. A planet with significant oxygen in its atmosphere, particularly if that oxygen persists over long periods, would be a compelling candidate for hosting life. However, oxygen alone doesn't guarantee life, and the absence of oxygen doesn't rule out life. Earth's atmosphere contained very little free oxygen for the first 2 billion years or more of life's existence. Early life consisted entirely of anaerobic organisms that didn't produce oxygen. Even after photosynthesis evolved, it took hundreds of millions of years for oxygen to accumulate in the atmosphere, because the gas initially reacted with dissolved iron in the oceans and with rocks before building up in the air. An alien planet might be teeming with life, yet have no oxygen signature if that life hasn't evolved oxygenic photosynthesis, or if oxygen-producing organisms haven't yet generated enough oxygen to overwhelm the chemical sinks that remove it. Methane represents another important biosignature, particularly in combination with oxygen. Methane and oxygen react with each other readily. In the presence of oxygen, methane breaks down relatively quickly through oxidation. For both gases to coexist in significant quantities in an atmosphere, something must be continually producing them faster than they react and disappear. On Earth, biological processes produce both gases. Photosynthesis produces oxygen, while certain bacteria called methanogens produce methane as a metabolic waste product. The simultaneous presence of both gases in substantial concentrations would be difficult to explain through non-biological chemistry alone. Methane itself can be produced abiotically through geological processes. Volcanic activity, hydrothermal systems, and reactions between water and certain rocks can all generate methane without life. But these sources typically produce methane at lower, steadier rates than biological sources. If observations show variable methane levels, perhaps seasonal variations suggesting biological activity that waxes and wanes with seasons, or if methane concentrations are higher than geological sources could explain, this would strengthen the case for biology. Phosphine burst into the biosignature conversation in 2020 when scientists reported detecting this gas in Venus's atmosphere. Phosphine consists of one phosphorus atom bonded to 3 hydrogen atoms, and on Earth it's primarily produced by anaerobic bacteria living in oxygen-free environments. Phosphine is quickly destroyed by ultraviolet light and chemical reactions, so detecting it in an atmosphere suggests something must be continuously producing it. The Venus detection remains controversial. Subsequent observations haven't definitively confirmed the phosphine signal, and some scientists argue that non-biological chemistry could produce phosphine in Venus's harsh environment. But the episode highlighted phosphine as a potential biosignature worth searching for, particularly on worlds very different from Earth. Ozone, a molecule consisting of 3 oxygen atoms, serves as a secondary oxygen biosignature. Ozone forms in atmospheres when ultraviolet light breaks apart molecular oxygen, and the freed oxygen atoms recombine into ozone molecules. Ozone is easier to detect spectroscopically than molecular oxygen, so finding ozone in an exoplanet's atmosphere provides strong evidence that molecular oxygen is also present, which in turn suggests photosynthetic life. Ozone also absorbs harmful ultraviolet radiation, protecting planetary surfaces from DNA-damaging rays. The presence of an ozone layer suggests not only that photosynthetic life produces oxygen, but also that conditions at the surface might be suitable for more complex life that would otherwise be sterilized by ultraviolet radiation. Nitrous oxide, laughing gas, represents another possible biosignature. On Earth, certain bacteria produce nitrous oxide as a byproduct of nitrogen metabolism. Like oxygen and methane, nitrous oxide is reactive and doesn't persist indefinitely in atmospheres without continuous production. Detecting significant amounts of nitrous oxide, particularly in combination with other biosignature gases, would strengthen the case for biological activity. However, nitrous oxide can also be produced abiotically through lightning, volcanic activity, and chemical reactions in the atmosphere, so its detection alone wouldn't be definitive. Sulfur compounds offer additional biosignature possibilities. Dimethyl sulfide, produced by marine phytoplankton on Earth, has a distinctive spectral signature. Hydrogen sulfide, while toxic to most Earth life, is produced by certain bacteria and might be an important gas in alien biospheres based on sulfur chemistry rather than oxygen. Carbonyl sulfide, though produced both biologically and geologically, might still serve as a biosignature when detected in combination with other gases in ways that geological processes can't easily explain. The key to biosignature detection often lies not in finding a single gas but in detecting combinations of gases that shouldn't coexist in equilibrium. Chemical disequilibrium, the simultaneous presence of gases that react with each other, suggests that something is continually producing those gases, driving the atmosphere away from chemical equilibrium. Life is inherently a disequilibrium phenomenon. Living organisms take in certain chemicals and energy, use them to maintain organization, and grow and excrete different chemicals as waste. This metabolism creates chemical imbalances that wouldn't exist in a sterile abiotic system at equilibrium. Earth's atmosphere is far from chemical equilibrium precisely because life constantly produces gases that react with each other and with the environment. An alien planet with life would similarly maintain chemical disequilibrium, though the specific gases involved might differ completely from Earth. The challenge lies in distinguishing biological disequilibrium from geological or atmospheric processes that can also create unusual gas combinations. Temporal variations in biosignatures provide additional evidence. Seasonal changes in atmospheric composition might reflect biological cycles, plant growth during spring and summer, dormancy during fall and winter. Daily variations might reflect photosynthesis, starting at dawn and stopping at night. Finding these rhythmic patterns would be strong evidence for biology because non-biological processes rarely produce such regular, predictable cycles tied to light and seasons. Surface features offer another category of biosignatures. On Earth, large-scale biological activity affects the planet's appearance in ways that might be detectable from space. Vegetation reflects light in characteristic ways. The red edge, where plant reflectance increases sharply between red and near-infrared wavelengths, as plants reflect infrared light they cannot use for photosynthesis. This vegetation signature is quite distinctive and might be detectable on exoplanets if vegetation covers substantial portions of the surface. However, alien photosynthetic organisms might not have a red edge. Plants on a planet orbiting a red dwarf star might be black to maximize absorption of the dim red light available, or they might be other colors, entirely depending on their star's spectrum and their photosynthetic pigments. Large-scale color changes across seasons could indicate biological activity. If part of a planet's surface changes color seasonally, perhaps from green to brown, as vegetation grows, and then senesces, this would be difficult to explain through geology alone. Detecting such changes would require extremely high-resolution observations across multiple seasons, pushing the limits of even the most advanced telescopes. But future extremely large telescopes might achieve this capability for the nearest exoplanets. Ocean glint patterns might reveal biological activity in oceans. Certain types of marine life produce compounds that affect water's surface tension or create surface films that change how light reflects off the ocean. These effects, though subtle, create characteristic glint patterns that differ from pure water. Detecting such patterns from light years away would be extraordinarily challenging, but might become possible with next-generation direct imaging telescopes. Atmospheric hazes created by biological activity represent another potential signature. On Earth, isoprene and other organic compounds released by plants contribute to atmospheric haze. On Titan, Saturn's moon, photochemistry creates organic hazes that give the atmosphere its orange color. Distinguishing biological from non-biological hazes would be difficult, but characteristic compositions or variations might provide clues. A planet with organic hazes that change seasonally, for instance, might have biological sources for those hazes. Artificial light on the night side of a planet would be an unambiguous technosignature, a sign not just of life, but of technological civilization. Earth's night side is bright with city lights, electricity use, and various artificial illumination. An alien civilization would likely develop artificial lighting at some stage of technological development, and if they use inefficient lighting that wastes energy by sending light upward into space, rather than directing it all downward toward the ground, their cities might be detectable. However, detecting such faint light from an exoplanet would require extraordinary capabilities beyond current technology, though future direct imaging telescopes might achieve this for the nearest, potentially inhabited worlds. Industrial pollution offers another technological biosignature. Chlorofluorocarbons, CFCs, are entirely artificial. They don't exist naturally and are produced only through industrial chemistry. Detecting CFCs in an exoplanet's atmosphere would be definitive evidence of technological civilization. Other industrial pollutants, nitrogen dioxide from combustion, sulfur dioxide from industry, certain combinations of gases that indicate smelting or chemical manufacturing, might also be detectable. However, some of these gases also have natural sources from volcanoes or other geological processes, so detecting them in amounts far exceeding natural production rates would be necessary to infer industrial activity. The challenge of false positives, non-biological processes that mimic biosignatures, looms large in biosignature detection. Every proposed biosignature has at least some possible abiotic production mechanism. Oxygen can come from water photodissociation. Methane can come from geology. Phosphine might be produced by unknown atmospheric chemistry. Distinguishing true biosignatures from false positives requires careful analysis of gas abundances, combinations, variations over time, and compatibility with the planet's other known properties. Context matters enormously. Finding oxygen in the atmosphere of a planet with a surface temperature of 500 degrees would not suggest life. The planet is too hot for liquid water and likely for any chemistry we would recognize as living. Finding oxygen on a planet in the habitable zone with liquid water on its surface would be far more compelling. Finding oxygen along with methane, nitrous oxide, and seasonal variations in atmospheric composition on such a planet would be extraordinarily difficult to explain without biology. The search for biosignatures requires sophisticated instruments that can analyze light passing through exoplanet atmospheres during transit. As a planet passes in front of its star, some starlight passes through the planet's atmosphere, and gases in that atmosphere absorb light at specific wavelengths, creating an absorption spectrum. By comparing the star's spectrum with and without the planet in front of it, astronomers can determine which wavelengths are absorbed and thus which gases are present in the atmosphere. The James Webb Space Telescope, launched in 2021, has the sensitivity to detect biosignature gases in the atmospheres of certain types of exoplanets, particularly those orbiting small dim red dwarf stars, where the ratio of planet atmosphere to star is more favourable. Future missions propose space telescopes like the Habitable Worlds Observatory or ground-based extremely large telescopes currently under construction will have even greater capabilities, potentially able to characterize Earth-sized planets in the habitable zones of sun-like stars, the most promising targets for finding life as we know it. These missions might detect multiple biosignature gases simultaneously, observe seasonal and diurnal variations, and potentially even directly image planets and analyze their surface properties. The biosignatures that reveal living planets encompass atmospheric gases that shouldn't coexist, chemical disequilibrium maintained by constant biological production, temporal variations that reflect biological cycles, surface properties that change with seasons, and for technological life, pollution, artificial lighting, and deliberate signals broadcast into space. Each signature provides a puzzle piece, and no single piece definitively proves life. But multiple signatures, detected together, in combinations difficult to explain through non-biological processes, could provide compelling evidence that we've detected life beyond Earth, transforming the ancient question of whether we're alone from philosophy into science, revealing that the universe contains not just planets and stars, but living worlds where chemistry has crossed the threshold into biology, where organisms grow and reproduce and evolve, where perhaps intelligence has emerged to contemplate its own existence and wonder, as we do, whether anyone else is out there among the countless worlds orbiting distant stars. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shock waves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Xio, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow, but there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons, and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun, they stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the sun to the distant reaches of space. When magnetic field lines from different regions of the sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the Sun's activity cycle. During solar maximum, when the Sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the Sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the Sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the Sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighbourhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe.